Right, my goal with this presentation is to introduce something called differentiable programming, which hasn't seen much take up in the D community, although there are some libraries. So I'm kind of do a basic introduction to some of the concepts, and then we'll go from there. There's a new word in the title, which is differentiable. So we see over differentiable programming, D. These are the main interesting words. We can work through them backwards. So D, we all know. If not, welcome to D. And programming, we also know this one, hopefully, even more than D, hopefully. However, that being said, it's worth keeping in mind that programming is not just programming. There are ways of doing things and ways of using things that shape how you program. And then differentiable, which is the new word, which comes from mathematics, that we can calculate rates of change and gradients of things. And this will be a way of programming where the quantities we output are explicitly given gradients that we can use. Which brings me on to gradients and so on. It's a common question to want to know, how fast does a train go? Or if I wiggle a parameter in my model, how much is the output going to change? Or rather, how much is the slope of the output at that position in the parameter space? And here's a kind of a practical example. This is some data I collected of me in a train, of the distance travelled over time. It looks vaguely synthetic, it is actually real. If you lay a triangle over the main dotted line, we can see that the speed, i.e. the change in distance over the time I travelled, is about 200 metres for every 5 seconds, so it's about 40 metres per second, which is like something near 100 miles an hour. And now, having looked at that, we now have some intuition about how to calculate a gradient. We can start looking at functions which we've specified just using symbolic mathematics, i.e. we have f of x equals x squared, which I've drawn in this sort of charmingly terrible diagram here in the middle, and we can calculate the gradient at any given point, very simply. If we just bump x with f, i.e. so we calculate f of x plus h minus f of x all over h. And it's actually not a very good approximation, but it'll do. So we can write a function called diff, which will calculate this for us, and we can run it over from -5 to +4. As you can see there, we can notice that the results look suspiciously like 2x, i.e. -5 going to roughly -10, -4 going to roughly -8. So the idea isn't there's some kind of approximation error there, but we can investigate. What we can see, if we actually expand the formula beforehand, so if we expand x plus h all squared to x plus 2xh plus h squared, and then divide by the h, what we can calculate is that we end up with 2x plus h. And if we set h to 0, i.e. we have a infinitely small wiggle in the x-axis, then we get 2x. So we've calculated some kind of symbolic rate of change, which we are going to call a derivative, which is where the differentiable comes from. And just for some bookkeeping, these are normally notated as df dx or f prime of x, so-called Leibniz and then Newton notation. So differentiable programming, then, is the way that we can write programs where the gradients of the output are free. So, we do x plus y, we get the gradients of x plus y with respect to x and y. There are languages that are built around doing that, but I think we can get it for free relatively easily in D. The key thing here as well is also that the answers will be exact. There will be no approximations. So we won't be doing any kind of something called finite differences, which is what we saw earlier. We also won't be generating code from some kind of symbolic specification, which we'll see at the end. And in practice, differentiable programming is often basically a euphemism for something called automatic differentiation. So we have the forward mode, which is very simple. You just basically just replace the normal doubles we'd use for doing mathematics with a new number type. And then the reverse mode, which is much more complicated but much faster when you have lots of parameters, and we will have a quick look at both. So forward mode automatic differentiation basically uses a clever observation about the rules of calculus, the rules of calculating gradients, so that we can replace our usual doubles with effectively a new type of number. And then when we use the function like normal with that new derivative, basically because of the magic of operator overloading, we can get the normal return value and the derivative. So we need some rules for doing calculus. The main ones to really pay attention to these ones at the bottom. You see we have product sums and the chain rule. The trick with automatic differentiation is to actually encode these on the numbers in this new special type of number, which we'll see next slide. But just the thing to notice is also none of these require anything non-local. To calculate the gradient of a plus b, we only need the gradients of a and b, for example. But the one that we really need is here is the chain rule. So if we have the derivative of f of g of x, then we have the gradient of that going to g prime of x times f prime of g of x. If we try this in anger, here's something called the steps annotated. We attack the main expression by breaking it down into two expressions, which are then summed, and then we've applied the chain rule on the left-hand side, and then this power rule, or rather the one we calculated earlier on the right-hand side, and then you can see we have, because of the chain rule, we've brought down this x squared, and then you can see it's just flipped it around there at the end. The observation, then put more formally, is that we can just store the value in the derivative and then encode these rules on the value of the derivative of each value, and then as long as we do the algebra right, we'll get an exact answer for the derivative at the end. And this was first noticed by Wenger in the 1950s, although this was in Fortran, so it wasn't operator overloading as much as you were either transforming the program entirely or keeping a second set of variables around everywhere, coding that manually, but the idea was the same. So the new type of number then, you can see here, is called a dual, or a dual number, where the dual number name actually comes from Clifford studying them in the late 1800s, but that's relatively unrelated to the modern usage. But we store the value in the derivative, and then we act on them as we need to for each operation. So we basically have rules, and then a few specific cases which we've calculated the gradients of on paper. So we see with the exponential, it maps its gradient to itself, but we need to apply the chain rule. So we have this const double new derivative bit here. So we have the new value, i.e. the exponential of the value, times the current derivative. That's the encoding of the chain rule. And then obviously the new value just calculates the exponential. So that's to itself. And then you have the chain rule that we saw earlier. And the draw is that if we use templates, we can use our code practically unmodified with these dual numbers, and then we can just get our magical gradient spat out at the end. But there's a slight question in that we have to choose what we initialize the gradient with for the initial parameter. So if you imagine we're saying x is equal to 2, but what does the gradient of x equal to? And well, this is called seeding, and what we need to do is to observe that the derivative of x with respect to itself is 1, so we can set that to 1, and if we had any other variables, their derivatives would have to be set to 0. Their derivative with respect to x is 0. So our final code then to run is this. So we have result, and then we've applied this dual number with the correct seed to result. And if we print it, then we end up with a dual of like 4.01 and then 3.92, which we can compare with the gradient we calculated a few slides back, and we can see that we got the right answer. There's a problem with forward mode automatic differentiation, which is that if you have lots of input variables, then you have to rerun it every single time with new seeds, which is extremely slow asymptotically. What you can do instead is something called reverse mode, where we actually build a graph of the expression that we are doing calculus on, and then we actually propagate the gradients backwards. What I have in front of me is a implementation of a really basic reverse mode automatic differentiation system. If we start at the top of this class value, we have the normal data and gradient that we saw with the forward mode, but we now have an array of important things. We have an array of the previous ones, i.e. things that this depends on. And then we have this delegate, which actually updates the gradient based on the previous. And it's a far cry from functional programming, but it works. And then we just have some debugging code, file and line, just so I can use that for error messages if something breaks. But we can see what we've got here in this operator overload is actually implementations of all the operations for the reverse mode. So I think it'd be informative to look at this. And you see the first thing, just a bit of bookkeeping. If the input on the right hand side of this operator overload isn't of type value, then I make it into one, just so we can keep track of it in the graph. If we look at plus, for example, we can see that our output value is going to be a new value. What we do with the normal arithmetic, this is what's called the forward part. So we do this plus data plus that plus data, and we say that it depends on this and the value that we either just took or created. And then for our backward mode, we have to update the gradient of the ones that depend on it with the gradient of our current output, because it would have been updated by the ones that come before it. More on that later. And you can see that these are all fairly self-explanatory. This one's slightly more tricky, but the trick with reverse mode, if we do some sort of simple calculation at the bottom, So I've done a squared plus b. The trick is you have to run this run backward thing, which will then, rather than the output containing all the gradients we want, what happens with the reverse mode is that the inputs have their gradients propagated back towards them. So the derivative of the result with respect to a gets put in a, and you can see I've printed these. And the trick to doing that is we have to build a topological sort, so any dependency comes after the thing it's underneath in the graph, and then we go through it backwards, running these backward delegates, which gradually, when it's done, will contain fully propagated all of the gradients through the graph. And you can probably see already how this is relatively expensive. If you count the allocations versus just working on structs, it's much more expensive in the small case. For the large case, not only can you scale this very far, you can also do optimizations on it. And if you're clever, you can also reference count the graph, which means it's much easier to free memory on the graphics card. Just as a little treat, I've chucked in something called a ReLU, which is that's all right there, it's a rectified linear unit. So if it's positive, then it goes to the number, and then if it's negative, then it goes to 0. This is what you'll see in the wild with things like sort of PyTorch and TensorFlow and JAX and so on. They're typically all intended for AI. They basically all do reverse mode automatic differentiation, with the caveat that everything here so far has been with numbers, pi and 2, whereas what you want for AI is to be able to actually do calculus on things called tensors, so effectively n-dimensional arrays. And there are different ways of going about doing this. PyTorch uses a very dynamic graph, so the graph is built up at runtime, which you can then do optimizations on, and you can fuse operations, whereas what TensorFlow does is much more set in stone and static, which is not winning industry at the moment. People want to be working on PyTorch. And then I thought I'd just mention it kind of just for fun, some things which aren't differentiable programming, even though they do involve derivatives. So first of all, we can have symbolic CAS, i.e. computer algebra systems. We'll have a look at one of those. That's basically not programming, but one thing that's kind of quite interesting is you can actually program with derivatives. So you have these things for doing systems modeling languages, where you encode a model in a kind of a simple kind of domain-specific language, and then it uses various techniques to work out what the consequences of those kind of differential equations, what those models mean. So this is an example from a Chilean cybernetics project in the 70s, which someone has very handily preserved, where they were attempting to model the entire Chilean economy in sort of 150 lines of this language called Dynamo. So I mentioned symbolic computer algebra systems. This is Mathematica, which is one of the the world's most famous and most profitable computer algebra systems. What I'm going to show you is just a really tiny demo of what it can do. So you can see what I've done here is I've just declared a little function called f of x again, which takes the exponents of minus x and adds it to sine of x. And also for reference, this just means it's a parameter, this underscore. And what you can see about its internal representations, you can see how it sees these expressions internally. So because it's symbolic computer algebra, what you can do is, so for example, if we want to calculate a gradient, then it'll just do it for us. Then also if we want to calculate an integral, i.e. the area under the curve, we can just do that. We can just do that too. And the important observation here is that I'm not sure for whether I'd actually call this programming, which is why I don't consider these differentiable programming. In this Wolfram language, there are patterns which you could recognize as programming, but I'm not sure if you could really call it a full-fledged programming language. It's not very resilient, so you'd be able to do it's Turing complete, and you could do things, but it's not really kind of a true programming language in its own right, I think. In the 70s, a book was written declaring the world might end at some point in the future. Take with a grain of salt. It's the result of a model that was written called World 3, and it was published in a book called The Limits to Growth. This here, thank you to bitplayer.org, is a implementation of that. Not in the original, it was also written in Dynamo. This isn't in Dynamo, this has been translated into JavaScript, but you can see if we run it, we end up with these complicated sort of dynamics of all these linked quantities, and we can adjust various things about the model. Now this is really not differentiable programming, because we're effectively just laying out relationships between things rather than actually writing programs as per se. Whereas in a Mathematica program we just saw, you would be able to say load data from a file and that kind of thing, whereas a language like Dynamo is really a very domain specific language.